All right, let's move on into section 2.7, which is going to be working with inverses of functions, which is going to be important to what we get later on in a couple of our chapters. Inverse of a function basically is kind of going backwards of what you've done going forward. So we've talked about inverses before, that how do I undo an addition? It is subtraction. How do we undo multiplication? It is division. So those are inverses of each other. How do I undo a square? Then we have to square root, okay? So many times in mathematics you are working with what we refer to as inverse, or as an inverse, maybe. When asked what is the opposite of addition, you say subtraction. What is the opposite of multiplication? You say division. What is the opposite of squaring a number? I just went over that. It is the square root, okay? So this is going to be applied to functions as well. So here's our little definition. We're going to let f and g be two functions such that f of g of x. So here's where composing comes into play. If I do that with those two functions, it equals x for every x in the domain of g. And the reverse of that, g of f of x equals x for every x in the domain of f. Therefore, the function g is the inverse of f. And the notation of the inverse of f is with this f to the minus 1. So make sure you realize that that's not really taking f to that power. It is just a notation thing. Now, the domain of f is equal to the range of g. So this is where we end up, or I'm going to say the range of g, which is also f inverse. So in parentheses, I don't want to use parentheses there. Let's see. Maybe I just write it. Which is also f inverse, okay? All right, so what we're going to be able to do, the domain of f, which are the x's, is the same as the range of g, which are the y's. So this is where we kind of are able to have that idea of swapping the x values in order to find some points. And we'll see that later when we are graphing, okay? So that's a key thing to remember, that the domain of f is also the range of g. All right, moving right along. So we have to confirm both compositions, this and this, have to equal x if these two functions are inverses, okay? So we need to find these compositions and determine whether each pair of functions f and g are inverses. So basically, if they're inverses, are they equal to x is what we're looking for. All right, so this is where our composing in the last section is going to help us out. I need to first, for f of g of x, I need to take the g function and place it into the f function. So first off, I'm going to put this in here, notation-wise. So I need to find f of x plus 7 all over 4. So all I'm doing is just replacing what g is equal to. And so now this f of x plus 7 over 4 means that I need to go to my f function and I need to do the rule. It says to take 4 times what's inside here and then subtract 7. So that means I need to take 4 times that x plus 7 all over 4 and then subtract 7. So 4 times what's inside there minus 7. And then I need to simplify. And when I do that, notice here, if I put this over 1, these 4's are going to cancel straight off, leaving me with x plus 7 minus 7. And these are going to cancel, which just leaves me x. That's good. If one of them works, maybe the other one will, maybe not, okay? If they both work, then they are inverses of each other. So let's try the other version. Let's go g of f of x. I'm going to take f of x, that 4x minus 7, and put it right in there. So this is equivalent to g of 4x minus 7. So now I need to take this and go to my g rule and figure out, take wherever this is to take what's inside here, add 7 to it, then divide by 4. So I'm going to take 4x minus 7, put it in for the x, 4x minus 7. Then it tells me to add 7 and then divide by 4. So the task now is to simplify this. And so, notice, I'm going to be able to cancel those 7s on the top. If I simplify the top and simplify the bottom and then cancel what I can, what I'm left with now is that 4x over 4. Notice those 4's are going to now cancel out and leaves me with x, which is good because since they are both equal to x, yes, f and g are inverses. Okay? All right. Now, here I gave you the two functions and said, are they inverses? And we just had to verify with our f of g of x and our g of f of x that they are both equal to x. But what if they only give you one function and say, find the inverse of that function? There's 4 small little steps that we have to take in order to do that. So here we go. We're going to replace f of x with y in the equation for f of x. Okay, so the original function, or if it's g of x, whatever the original function is, remember that f and g we can interchange. We're going to take that away and make it a y value, okay? Then we're going to interchange x and y. Now, the reason we can do this is because by definition, we had, remember, it said that the range, or that the domain of f is the same as the range of g. So that means we can switch those two values there. So we're going to interchange x and y. So if we do that in this one, I'm going to take y, make it an x. Wherever I see an x, I'm going to make it a y. And then we're going to solve for y. And then we're going to replace y with f inverse of x because that's really what y is now. It is the inverse of that. All right, so we've done step 1, replace f of x with y. We've done step 2, interchange the x's and y's. Now let's solve this equation for y. If I want to get y by itself, first I've got to get rid of this plus 7. So I'm going to subtract 7 from both sides. I get x minus 7 equals 2y. Then I'm going to divide by 2. On all cases, now you can divide all of that by 2 or each individual. It doesn't matter which one. This is going to cancel, leaving me with y equals x minus 7 all over 2. Now, I'm going to then just make that final little note here, do that f inverse of x. So that is what, of my original function, this is the inverse of that. Okay? All right, let's do that on this next one. Here I have g of x this time, so we're going to find g inverse. I'm going to take out the g, replace it with y. That's step 1. We're going to now interchange x and y. So wherever I see a y, I'm going to put an x. Wherever I see an x, I'm going to put a y. And then we're going to solve for y, which is step 3. Here's where y is. I need to get rid of this minus 1, so I'm going to add 1 over, which looks very similar to the last process. Then I'm going to get y by itself again by dividing by 4. So that goes away. Now instead of just having y this time, now I have y cubed equals x plus 1 all over 4. So this gets to the idea of how do I undo that cube? Well, if we had a y squared or an x squared, we would square root both sides. When I have a cube, to undo a cube, that means we have to do the cube root function. So if I do the cube root of both sides, and the cube root of this, remember this power and that index is going to cancel themselves out, and just leaving me with y underneath there is equal to the cube root of x plus 1 all over 4, and that right there is our inverse. And so, because we started with a g, I'm going to say that the g inverse of x is equal to the cube root of x plus 1 all over 4. And that's going to be our final answer. Okay, so remember, undo, 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 solve, solve, solve for y. Okay, so hopefully those aren't too bad with the 4 little step process there. Okay, now that is if we are finding the inverse, which means that we should already have known that the inverse exists. Now, not all functions is there an inverse that exists. Now, we've previously seen the vertical line test to determine if a relation is a function, which means that if I were to draw any vertical line through, it only has to intersect that function in one spot for it to be, or the relation in one spot for it to be a function. Okay? Now, what we have is another test that we can do in order to determine if a function has an inverse, okay? And so now we're not looking at the vertical line test, we are looking at the horizontal line test. So, a function f is going to have an inverse that is a function, we'll call it f inverse, if there is no horizontal line that intersects the graph of the function f at more than 1 point. Okay? So we have to, first off, it has to go vertical for it to be a function. Okay? If I now, each one of these are functions, if I now look and go horizontally and it intersects in more than one spot, which also we can look at a parabola, horizontally there are 2 spots that it intersects, there is no inverse here. It can only intersect it in one spot for it to have an inverse. If I go with the horizontal line test here, no matter where I draw that horizontal line, it's only intersecting it in one spot on that function. So yes, we have an inverse here. If I look at this one gets real tricky when you get down here. You have to remember that with rational functions, that this is just approaching, and it gets smaller and smaller and smaller. So actually, yes, this is only going to intersect it in one spot. So each one of these has an inverse, except for this first one, and then the one I just added with the parabola. Okay? So that's graphically an easy way for you to be able to determine yes or no. So in the definition of an inverse function, it is said that the domain of f is the same as the range of the inverse of f. This means to get the point, so we're going to actually now give a graph. Can you graph the inverse of that? That's where we're leading on these last couple problems. So this means to get the points of f inverse, one just has to switch the x's and the y's of the original function. 2 functions which are inverses of each other will be reflective over the line y equals x. X, which is the line that bisects the first and the fourth quadrant. That is the line. That's our mirror. That's what it's going to be reflective over, okay? So when we had symmetry and stuff, we had reflection over the y-axis being symmetric and such. But here, we're now going to use this as our mirror. So that's going to be helpful for when we look at these next little pieces here. We're going to use this graph to draw the inverse function for that graph. Now, I'm going to call this graph f, okay? And it has 1, 2, 3 designated points on there. If I'm going to draw that inverse, that's going to mean that I'm going to have the y equals x line that is its mirror. And we need to figure out what the points are, okay? So for f of x, here are our points. This is the easiest way to do this. I'm going to graph or write this point. That's negative 3, 0. This point is negative 1, 2. And this guy over here is the point 5, 3. Now, in order to, well, we call it g of x, which is f inverse. In order to find the points on that, because the domain of this function is now the range of this function, and the range of this function is the domain of that function. Here's where we can just swap the x's and y's and now get new points of the inverse. That is the key thing, okay? That is the key to figuring out how to graph the inverse. So now all I need to do are to plot these points, and I'm going to do it in a different color. I'm going to do it in blue. Blue is going to be the inverse here. And so 0, negative 3. Don't go anywhere on the x, but go down 3. Then I get 2, negative 1. And I have the point 3, 5, which would be this guy up here. Okay? When I connect those, that is f inverse. And so notice it does, if I was more accurate with my y equals x line, it would mirror image. This ends up having, this guy right here is the same distance over here, this guy and this guy match up, and these 2 guys match up as well. And so again, that's the easiest way in order to graph a function given points. Okay? All right, and our last problem that we have for this section, kind of a shorter section here, we want to find an equation for f inverse. We're going to graph f and graph f inverse on the same rectangular coordinate plane. Again, we're going to have this be a mirror. And we're going to use interval notation to give the domains and ranges of each one of those. So remember, the domain of f is the same as the range of f inverse, and the range of f is going to be the same as the domain. So these are going to be the same, and these are going to be the same. Just a nice helpful hint. All right, so let's graph this guy. Actually, I want you to find the f inverse first, so we'll do that. Here's our function, x squared minus 1, and I hope you recognize that as a parabola that has been vertically shifted down 1. So I could graph that, but we have a restriction here that we only want greater than or equal to 0, okay? We're not going to use that just yet to find our f inverse, but we will use that when we graph, and I'll tell you why we need that. So let's go back to our 4 easy steps to find the inverse. So I want to take this, exchange that f of x for y. Then I'm going to switch my x and y's and solve for y. So I need to get rid of that minus 1. So let's add 1 to both sides. So we get x plus 1 on the left equals a y squared. And then in order to square or undo that square, that means I have to have a square root of both sides, okay? So I need to square root both sides, and I'm going to kind of do a little swap here. When I square root both sides of an equation, remember there's a plus and a minus there. So I basically have y equals plus or minus the square root of x plus 1. Now, I want you to remember this, that if x is greater than or equal to 0, that is in the f function. Remember when I swap that the domain of my f function is the same as the range of my inverse. So that means that if I interchange that x and y, that means that the range of f inverse has to be y to be greater than or equal to 0. So let me say that again. Because the domain of f is the range of f inverse, we can symbolize by doing the switch of our x and y's that if x is greater than or equal to 0 in the domain of f, therefore the y is greater than or equal to 0 in the range of f inverse. Now why is that important? Because then I come back to here, I do not want both of these. I cannot have both of these. I can only have one of those, okay, when you're working with inverses. So for y to be greater than or equal to 0, that means I have to choose the positive version. Choose the positive. So here, f inverse of x is going to be the square root of x plus 1. Okay, now hopefully I can convince you graphically as well. So if I have a parabola of a vertical shift down by 1, that means I go down 1, and our key points for a parabola, if you recall this, we had 0, 0, 1, 1, 2, 4. That meant I went over 1 and up 1, over 2 and up 4. 1, 2, 3, 4 would be here. Now, the whole parabola, I also get these points, okay? So this is the whole parabola. Now, why can I not have the whole parabola? That is this piece right here, where that comes into play. If I have the whole parabola, I try to do the horizontal line test, bam, it hits 2 points everywhere except for this vertex right here. Therefore, the whole parabola would not have an inverse, okay? That's why I have to put a restriction in here that I want all x values that are positive. So I only want this portion of my parabola. So I cut half of it off basically, and now I can talk about the inverse. So I'm going to do that, cut that off, and come back and tidy it up a little bit. Okay, so this is going to be the parabola that I am going to now have an inverse for, okay, which we found it. It is that square root function. If we go back to our transformations where I have the plus 1 inside with an x, I have to take the opposite of what I'm looking at. That means I'm going to have a horizontal shift to the left of 1. So it would be negative 1. So that means I have to go over here at negative 1. Now, remember what the key points were for a square root. The key points for a square root were very similar, except for now notice, oh, these two are switched. 2, 4, 4, 2 down here. So I need to go over 1 and up 1, and over 4 and up 2. And that gives me my version there. Let me change the color here so you can see it. So this point, and this point. And so when I do that graph, notice that that line y equals x is the one that actually does split it as its mirror. So coming back into play are some of these graphs that we looked at, so make sure that you do that. Or, worst comes to worst, you can always plug in numbers into a function that you have. So pick numbers and plug them in. Now this is kind of the generic from the original, and I was just moving side to side. That doesn't go actually into that. But nothing says you can't do a t-chart in each one of those and figure it out that way. Okay, so let's talk about the domain of f. The domain of f kind of comes from this restriction, and if graphically on the x's of my f, here's f, I'm at 0, and everything beyond that gives me a number. Okay? Now, the range of f means that now I look vertically. Well, nothing until I have -1, and it goes to infinity at -1. So here we have -1 to infinity for the range of f. And if I look at the domain of f inverse, now that I have a graph of f inverse, it makes it a lot easier to see. Well, if I come along my x's, nothing here until I get to -1, but there is something along this way from -1 to infinity. And the range of f inverse coming in the y direction, now I stop here at y equaling 0, and there will actually be something forever and ever and ever, and we'll go very, very slowly, but there will be a y value for everything. So from 0 to infinity, I have the range of f inverse. Now, what did I just say earlier? These two are going to be the same, and these two are going to be the same, and we just proved it by the graph that they were. Remember, the x values of f are the same as the y values of f inverse, and the y values of f are the same as the x values of f inverse. And so there we have it. That is with our inverse functions. We will go on to our next section. As you see down here, it is about distance and midpoint formulas. So this is kind of the extent on of chapter 2 as far as we go into our functions at this point. So until next time.